Our next speaker, thank you, Aaron. Our next speaker is Maryjo Brounce. Maryjo is assistant professor at UC Riverside in the Department of Earth and Planetary Science. She joined UCR in 2014 after a postdoc at Caltech and a PhD at Rhode Island and the Smithsonian Institution. She's an igneous petrologist and analytical geochemist interested in the composition of the solid Earth, Moon, Mars, and the extent to which planetary interiors and exteriors interact during various rock-forming processes. Maryjo.
Okay, thank you. Thanks for the invitation, and thanks everybody for tuning in today. There were a variety of things that I could talk about, and in the end I decided to focus specifically on iron-XANES measurements of silicate glasses from Earth because I thought there was enough there to talk about for people who might be interested in or new to doing these kinds of analyses that I'd share what I have learned so far. So I'm going to show you measurements that I do of samples. Aaron referenced them briefly in his talk, these somewhat rare melt inclusions inside mineral hosts. And this is a picture of one hosted inside an olivine on the left-hand side. And then I'll show you how we also apply these kinds of measurements to any kind of glassy pillow lavas that you can dredge or drill off of the ocean bottoms in order to learn something about the availability of oxygen in the solid Earth. And I just wanted to take a minute at the very beginning to make sure we're all on the same page and we understand what we're talking about when we say the availability of oxygen. So this is a list of the 8 most abundant elements in the bulk Earth. You see that oxygen is on this list and it's really high on the list. And this is a really important point. There's an enormous amount of oxygen bound in the solid Earth and in the solid rocky planets of our solar system everywhere. Oxygen is a little bit different than everything else on this list because it primarily serves as the anionic balance to the cation versions of all of the other elements on the list. So for instance, we also have an enormous amount of silicon bound in the solid Earth and the other rocky planets, but it's not there as silicon metal. It's there as silica 4+ as a cation, and there are 4 oxygens hard bound to most silica cations. It forms the silica tetrahedron, and of course this gives rise to the great mineral diversity, the silicate mineral diversity that make up the mantle and the crusts of all of these rocky planets. So what we're interested in talking about is when we're thinking about oxygen is not the abundance of oxygen. We know that there's a lot of it, but which of that oxygen is available? And so for instance, these 4 oxygens that are bound to the silica cation over here on the left, those oxygens are not available to participate in reduction oxidation chemistry. Similarly, the oxygen that's bound to magnesium, which exists predominantly as magnesium 2+ in the solid Earth, those oxygens are not available for reduction oxidation chemistry. So even though we have an enormous amount of oxygen, a vanishingly small amount of it is available for inorganic chemical exchange. And this is really different from the atmosphere, where there's much less oxygen present at Earth's surface in the atmospheres and oceans, but what is there exists predominantly as the dioxygen molecule, and this is very reactive, and so it's very available and readily reacts with structures that we build with metallic iron and oxidize them to ferrous and ferric iron, and we see this as rust with our eyes on the time scale of decades to centuries. Okay, so then if we want to look at not what is the abundance of oxygen bound in the inner solar system, but what is the variation in the availability of oxygen in all of these rocky planets in the inner solar system, it would look something like this, where we're keeping track of the log of the partial pressure of the dioxygen molecule. And so Earth's atmosphere, for instance, hangs way over here to the right at 1 atmosphere at sea level. We know that there's about 0.2 atmosphere oxygen present. And so the log of that number is something like minus 0.6. And so it's way over here to the right-hand side of the diagram. In comparison, the solid bodies, the solid Earth, solid Mars, Venus, Mercury, the Moon, all have many orders of magnitude lower available oxygen. So these partial pressures of oxygen or the fugacity of oxygen in the solid planets are much, much lower. And so we start getting into realms of reduction oxidation chemistry that we don't expect in surface or low temperature environments that we'd been talking about earlier here. I'm also going to just briefly define a reference frame just to keep in mind. I'm going to use something called the quartz phaelite magnetite solid oxygen buffer just as a reference frame here a little bit later in the talk. And really what's important to know is that QFM has some kind of intermediate value here that we expect for solid planets. And I'll reference on this log scale above or below that value so that if I wanted to talk about the activity of oxygen at Earth's atmosphere, which is 7 orders of magnitude higher on this log partial pressure uniaxial diagram. I could say QFM plus 7 as shorthand, so that we're not talking about differences of very small numbers. The only thing to keep in mind here is that anytime I have a +1, -1, -4, these are log order of magnitude changes and variations. And so you see a really big swing in the extent to which oxygen is ready to perform reduction oxidation or drive reduction oxidation chemistry in these solid materials. Okay, so we look at this distribution in the inner solar system, and what really draws any geochemist's eye here, I don't think that you need to be a high temperature geochemist or igneous petrologist to start asking questions about this variation. And one of the most eye-catching things is this really wide range that the solid Earth records, that it gets as reduced as the most reduced stuff that we find in the solar system, the moon and perhaps Mercury, but it also gets very oxidized, very significant amount, a high amount of this partial pressure activity of oxygen. And of course, Earth's atmosphere is way over here to the right, where we've got this dioxygen molecule to a first order because of the presence of oxygenic photosynthesis. And so that is the presence of life. And so there becomes these kind of really profound, kind of fundamental questions to understand how long has Earth had this widespread in the activity of oxygen recorded in the solid body? And is there any role of the arrival of life at Earth's surface or the arrival of hydrous conditions at Earth's surface in generating this widespread, which we don't see to date in any of the other solid planets in the inner solar system? So we know something about this spread, right? The most reduced parts of the Earth, we know that our core is made out of metallic iron. And so we know that the very lowest partial pressures of oxygens recorded here are down deep in the deep interior. We also have a pretty good record of the activity of oxygen in the upper mantle, and this comes through classic studies of mid-ocean ridge basalt. It's kind of the simplest igneous rock system you can look at. And so we have a fairly good understanding, and I think broad community agreement about the FO2s that the upper mantle records. Again, broad understanding and consensus that the atmosphere has these very high partial pressures of oxygen because of the presence of oxygenic photosynthesis at Earth's surface. And the question mark here is whether or not we are drawn to higher values above kind of the normal upper mantle that we sample at mid-ocean ridges by some kind of interaction with the surface environments. Is there a role for the imprint of life at Earth's surface in generating the kind of high end of the range of high availabilities of oxygen in the solid Earth? And this is really one of the very classic problems in igneous petrology, is to understand and constrain plate tectonics. And in particular, this question gets at the subduction zone or the convergent margin end of plate tectonics. So here's a cartoon for anyone who's not sort of thought about this kind of scale for the Earth in a while. This is a mid-ocean ridge basalt over here on the left, and the idea is that we create the ocean floor out of the relatively reduced, the relatively low FO2 conditions of Earth's upper mantle near that value that I was talking about of QFM. And then it spends today an average of 65 million years in contact with the oxygen-rich and hydrous conditions of Earth's surface, up here at about 7 orders of magnitude higher activities of oxygen than the solid interior. And those imprints, that gets imprinted on the slab. We oxidize the ocean crust as it travels across the bottom of the oceans. And so we know that we deposit oxygen in the form of carbonate, for instance, and we take ferrous iron in the altered oceanic crust and the serpentinite slab lithosphere, we oxidize it to ferric iron, and we create the rust minerals. And then oceanic plates come to convergent margins, which I'm showing you here, and they subduct beneath subduction zones. And above those slabs globally, we always find arc volcanoes and sometimes back arc spreading centers. And as the pressures and temperatures squeeze on the slab as it enters the Earth's deep interior, signatures of that surface environment get squeezed out of the slab, and they contribute and make really characteristic imprints on the major element, trace element, and isotopic diversity that we see at arc and back arc volcanoes, which in a really typical way, a really classic way, distinguish them from mid-ocean ridge basalts. And so we are trying to answer this question: to what extent are the chemical fingerprints of Earth's surface environment communicated to the Earth's deep interior in subduction zones? And in particular, there's a very long-standing observation for 100 years or more that, in general, the basalts that erupt at arc volcanoes are more oxidized than those that erupt at mid-ocean ridge volcanic centers. And it has been a problem, a persistent problem in our ability to understand why that's the case, because our ability to measure the relative oxidation states of lavas that erupted arc basalts had been limited for a long time to kind of bulk rock analyses. And that stopped us because arc volcanoes form these big subaerial edifices because there's a lot of a magma supply there. You end up erupting lavas to 1 atmosphere pressure, and in that time they degas all of their water, their carbon dioxide, their sulfur. That gets degassed to the atmosphere and actually forms a pretty important input to atmosphere chemistry on geologic timescales. And you'll also notice the way that this cartoon is drawn, that the crust here underneath of that built volcanic edifice at the arc is really thick crust. And so the amount of cooling and crystallization and magma mixing and assimilation that these magmas do as they have to transit the relatively thickened arc crust as compared to mid-ocean rich basaltic crust might be a reason that we begin to oxidize these magmas. So it's been really hard to tease apart these details. Is it because the arc crust is thick here? Or is it because we know that we oxidize the plate before it goes down and those oxidized signatures get brought back up? And so that's a really important question. If we are taking oxygen fundamentally present at Earth's atmosphere because of oxygenic photosynthesis, we're storing it mineralogically in the slab, we'd like to know the extent to which that gets recycled and re-emitted to the surface, or if we've been subducting that very deep into Earth's interior and storing it there on geologic timescales. That's an important thing in terms of constraining the impacts of plate tectonics on igneous petrology and the composition of the surface environment. Okay, and this is where synchrotrons become very important. And so what I am going to do is use X-ray absorption near edge structure spectroscopy to solve this problem. And so this is a floor plan of the National Synchrotron Light Source 1. This is where I began my synchrotron education. It's now offline and we've transitioned to the advanced photon source, and I have a couple of slides here that get into some things that people should be aware of if they're really into reading any of that early work that came out of NSLS. There's a couple adjustments that everyone should be making as we work at APS and the NSLS2 and beyond. So these are, here's a figure of iron XANES spectra on silicate classes. And these are spectra that come from Andrew Berry, who was an early leader in the 21st century in the application of this analytical technique to silicate class. On the right-hand side, you're seeing what the known iron 3+ to total iron ratio is of these glasses. So the spectra on the bottom is very oxidized, almost 100% iron 3+, and the spectra on the top is very reduced, almost 100% iron 2+. This is the K alpha absorption peak for iron. So if anyone is doing conventional microprobe work and looking for iron there, this is the peak that you're looking for in order to quantify iron in your samples. And you can see generally as you look at the full XANES spectrum, how the shape of that spectra changes as the oxidation state changes. I'm showing you the first derivative of the spectra over here on the right-hand side that can make it a little bit easier to see how dramatically various features in that spectra are changing in response to the change in the oxidation state of iron. In particular, what we're interested in is in this little blip that happens before the K alpha absorption feature. This is called the pre-edge. And the pre-edge is where we're gleaning all of that redox information. And so we collect the full spectra, but we're really focused in a really narrow, about 4 or 5 electron volt range that occurs right here. And I've blown it up over here. So now these are pre-edges of a series of 1 atmosphere anhydrous standard glasses that Liz Cottrell made and are available from the Smithsonian collection for anyone to borrow should they be interested in making these kind of analyses. So these are meant to be standard glasses. And again, you can see this pre-edge feature is roughly a contribution of 2 Gaussians, a lower energy Gaussian and a higher energy Gaussian. And you can see that the dominance of the lower energy Gaussian diminishes as the oxidation state of iron in the glass increases. And in turn, the higher energy feature grows at the expense of the lower energy feature. I am showing you here on the right-hand side, again, known iron 3+ to total iron ratios of those standard glasses. What you'll notice is that there are 2 columns here. And this is because in any kind of analytical approach, you would like to know independently from this new technique that you're working on, what is the value? How do you define your standard classes? And so these are two approaches from Zhang et al. In chemical geology in 2018 and Berry et al. In the same year in EPSL. They're both Mossbauer based calibrations. And so these are values that we know from Mossbauer spectroscopy. So go away from the synchrotron, do Mossbauer the way you think you need to do Mossbauer, and come back with your known 3+ to total iron ratio. Then measure it at the synchrotron, collect your XANES spectra, and here's how your XANES spectra are varying. So quantify something about the shape of this pre-edge feature and relate it to the known 3+ to total iron ratio. There is an evolving conversation about how we should be doing Mossbauer and how we should be handling Mossbauer spectra. And that's why there's two values here over here in the right-hand column, is that there are a couple of different ways that you can reduce your Mossbauer spectra. And depending on which way you choose, you are going to end up with a different calibration line. And so you're going to end up with different 3+ to total iron ratios for your unknown samples. I'm not going to tell you which is the right way to do it because I don't know much about Mossbauer spectroscopy, and it's a really difficult problem to solve, it turns out. But you should be, anyone interested in this kind of stuff should be really aware and be able to and look at these two papers really carefully, and maybe even consider both in tandem while the conversation plays out. Okay, so that's great. We have the synchrotron. It lets us create these really beautiful pre-edges. I should say that a lot of the work, I think I did say that a lot of the work was at NSLS that I'll show today, but we do this work at the Advanced Photon Source at 13 IDE with the help of Steve Sutton and Tony Lanzarotti and Matt Newville. The thing that we get from the synchrotron is a very small analytical footprint. And so analytical footprint that's at the same scale as ion microprobe or FTIR or Raman or laser ablation analyses, which means we can now access at a small spatial scale the iron oxidation state inside silicate glasses. And that means that we can look at these kind of rare samples called olivine hosted melt inclusions. And so I've got two more pictures. I showed you one on the title slide. Here's two more pictures of these kinds of samples. These are olivine crystals. They are doubly polished so that they end up being like thin sections of single olivine grains. And the melt inclusions, they're doubly polished thin enough, so like on the order of 20, 30, 40 microns thick. They're doubly polished thin enough so that these glass inclusions are doubly exposed on both the top and the bottom. So just like FTIR works, so that we can take the synchrotron beam, which will pass through the depth of the sample and interrogate the iron oxidation state specifically in that glass volume. Now, the important thing, the reason we would want to get at measuring these melt inclusions is that they're trapped in these olivines. These olivines happen to have relatively high forsterite contents, and so these are really magnesium-rich olivines. And the kind of igneous petrology detail here to know is that olivine is frequently the first mineral on the liquidus. It's the first thing to crystallize as a melt of the mantle enters the crust and begins to cool. So the idea is that if these melt inclusions are trapped in the olivine as the olivine is growing, and the olivine is the first thing to grow, if the olivine can isolate those melt inclusion compositions from the evolving magma on the outside, we're able to capture now the oxidation state of iron in the very earliest stages of crystallization and differentiation. So like at the major element compositions that we routinely erupt at the mid-ocean ridge, where we're just sort of constantly erupting magmas very quickly. So in this way, we're going to be able to see through that significant crystallization and mixing and assimilation and degassing problem that happens at arc volcanoes, so that we can ignore that end of the process and see what is the oxidation state of these magmas right as they come out of the mantle. Are they oxidized already? Because that suggests a really solid link between those oxidized surface-derived materials being re-emitted at arc volcanoes. We're also able to make these measurements on these nice pillow lavas. So here's a pillow lava from the Western Equatorial Pacific. And if you were to thin section this glass in the same kind of way, you'd get something like this. And so you see that even in this beautiful, glassy, fresh sample, when you polish and you look at it under magnification, you find that there's a bunch of little quench crystallization everywhere. And if you were to take that whole glass and dissolve it to do these kind of historical measurements of the oxidation state of iron, you'd be interfered with whatever iron is bound mineralogically in these little crystals. And so we're able to very precisely and specifically measure the iron oxidation state in the silicate glass, which is our best analog for the liquid when it's molten. And so that's the real innovation here, and that's what synchrotrons allow us to do. Now, there's a major hurdle for this kind of work, for these kind of fragile silicate glasses, and that is beam damage. Okay, so I'm going to show you a series of plots. The y-axis is going to be the centroid of that pre-edge feature. So if you were to take the energy position of the low energy Gaussian and the energy position of the high energy Gaussian, and you were to average those two, you'd come up with the centroid energy of both of those Gaussian peaks. And in general, you can see that the centroid energy shifts to higher energies as the oxidation state of iron in the sample increases. And so these are the known iron 3 plus to total iron ratios from Mossbauer spectroscopy for the set of anhydrous glasses that I showed you the pre-edges for on the last slide, and a series of glasses from Roman Botchkarnikov. These are, I think, internally heated pressure vessel glasses with a range of water contents. These are data collected at NSLS. This is the NSLS1, not the NSLS2. And I'm showing you here the photon dosage. We were working at something like 10 to the 7 photons per second per square micron at that facility. That facility went offline and we transitioned to 13 IDE at APS, where the photon dosage is more like 10 to the 13 photons per second per square micron. And what you see is that the anhydrous glasses plot directly on those measured at NSL. So that's great if the glass has no water in it. But any of the glasses that have water on it return higher centroids than at the case for NSLS. And this is kind of a tale of NSLS versus APS, which you can read about in this American Mineralogy paper in 2018. But you can also go to the work of Ollie Shortle to hear about this process at Diamond, and also this 2020 chemical geology paper to hear about it at Soleil. So this is a little bit of a universal phenomenon as we move forward in the 21st century. And what's happening is that as the sample gets exposed to the beam and we're giving it a kind of photon dosage, we are artificially increasing the ferric iron in the glass. And so we're building the contribution from the ferric iron peak that has nothing to do with the way the volcano works and everything to do with what's happening literally in the hutch as the seconds tick by. And so here you can see, if you just park it at a particular energy, you can see how you, at the ferric iron peak position, you can see how that peak will grow in intensity as time goes on. This is all done at the APS, and what I'm showing you is that all hope is not lost, because you can basically attenuate, you can kind of dumb down 13 IDE to look like X26A at NSLS, the kind of work that we did in the beginning. So you can go from 10 to the 9 photons per second per square micron, dial it back to 10 to the 7 photons per second per square micron, and you see that the effect is diminished, kind of damped. So if you combine some combination of attenuating the beam before it hits your sample and defocusing your beam, 10 by 10, 20 by 20 micron spot, you can diminish that photon dosage. You want to be in the order of about 10 to the 7, 10 to the 8. And when you do that, you can get even hydrous glasses to continue to plot along kind of NSLS-like centroid positions. So it's something to be aware of. It shouldn't stop us all in our tracks. We can still come back to these kind of questions. Plate tectonics, what's the importance of it in subduction zones, and in particular with respect to redox chemistry? We went and measured a bunch of these melt inclusions and pillow glasses very carefully, and I'm showing you some data here on the left-hand side. Iron 3 plus a total iron on the Y, and I'm calling this is a barium lanthanum ratio here. It's not critical, just know that as you move away from this field of black circles, these are mid-ocean ridge basalts, it requires, as you increase your barium lanthanum ratio, it requires that there's an influence of surface materials in the mantle. And you can see that as you require the presence of surface materials to explain trace element geochemistry, something we've agreed upon for 30 decades or so in igneous petrology, you increase the oxidation state of iron in those glasses. And again, these are all at very kind of parental compositions. And so that's before crystallization and degassing has happened. And so we're able to firmly link then that subduction related basalts become more oxidized as the result of contributions of surface derived materials in the mantle. And so we can really use synchrotrons to solve these kind of old problems in igneous petrology. We come back to this plot in understanding what is the availability of oxygen, what is causing this range in Earth that we don't see anywhere else in the inner solar system. And we can answer that question and say it's plate tectonic mixing, and fundamentally seems to require that we introduce materials produced from the reduced interior of the Earth, expose them to the oxidized conditions at Earth's exterior, and then we physically mix them back down in the mantle. This means that if we're doing oxygenic photosynthesis to put oxygen into the atmospheres and oceans for the last at least 500 million years, then for at least 500 million years, we've been mixing those signatures back into Earth's mantle, and they are being recycled and re-emitted through arc volcanism. Okay, and so there's a really kind of fundamental impact of the arrival at life at Earth's surface and a primary mode of igneous differentiation, which are the oxidized arc basalts today. So that's really exciting.
I need to finish up now.
Perfect. This is what I have. This is what I can tell you that I'm learning about synchrotrons and geochemistry. I think this has been said a whole bunch of times, but I'll repeat it. Synchrotron source S-XANES measurements are powerful tools, and we can readily get at classic problems in spectrology here in ways that we have been kind of stuck in the mud, so to speak, for a while. They happen at the same spatial scales as SIMS, microprobe, FTIR, Raman, laser ablation analyses. So if you kind of carefully order all of your analyses in a row, you're able to kind of layer on redox information to a full suite of major trace, volatile, and isotopic measurements. And that is real power in analytical geochemistry today. Major caution sign, beware of beam damage, particularly for high silica and hydrous classes, and have a plan to test this and be ready to demonstrate it. And importantly, for this work on iron, S-XANES, and silicate classes, more photons and smaller beams are not advantages. And this is true for most work relevant to silica and water-rich compositions of terrestrial igneous rocks. It can get in your way even for mid-ocean ridge basalts if you're not aware of it. So go read those papers really carefully. They'll be really important. And there are 2 Mossbauer calibrations happening right now for iron S-XANES work, and you will end up with different ferric to ferrous ratios for the same measurements, depending on which approach you decide to go with. And I kind of lightly suggest that perhaps we should be considering both approaches in post-processing right now as that conversation evolves.
Okay, thank you. Oh, sorry. Sorry, I didn't mean to cut you off. My computer crashed briefly during your presentation. So all that means is if there were questions in the chat, I might have lost them, but there are a couple of questions. So why don't we're a little late, but let's take a couple of questions anyway. One is from Paul Fenter. Have you tried using fast measurements, short exposure, lots of detectors to avoid beam chemistry issues? Do results relax to the correct values after the fact?
Yeah, so we're using detector arrays, and that has shifted around a little bit as hardware at NSLSN APS has changed a little bit. But there's a series of 4 silicon drift detectors that we're using. And so that helps because, we can stack all those spectra. We are kind of at the limit of how fast we want to go. And that's because if I can really quickly just bring that back up, if you look at the difference in energies for the pre-edge features, here, right, that low energy Gaussian and high energy Gaussian peak, they're only about 1.5 or 2 electron volts away. So you really do you're going to need to have some kind of basic amount of basic quality signal to noise in order to do this precise work really, really well. The other thing too is that the whole dynamic range that we're interested in, everything on Earth, the lowest values, now these absolute values will change depending on whose Mossbauer calibration you want to go with, but the difference in the most reduced and most oxidized stuff erupting today is only about 10 or 15% absolute. So yeah, those are all great strategies, but there'll be a limit if you want to do really precise measurements.
Okay, so I think we're getting a little bit behind, so I think we should move on. But there's another question from Satish, at least one more so if you could please answer that one in the chat. Okay, great. So let's move on to the next presentation. Thank you, Maryjo. Great presentation.